everyone. Hello everyone. First of all, I would like to thank the organizers of the TXRF Club for the invitation. I have worked with TXRF during the last part of my PhD, during a pre-doc stay in Hamburg under the supervision of Professor Ursula, and also during the last part of my postdoc. Here I will present the publications of our research group in relation with the preconcentration strategies using nanomaterials prior to TXRF during the period 2013 to 2020. This is the index that we are going to follow. First, we are going to have a brief introduction. Then we are talking about microextraction and preconcentration strategies. Then we will focus on sample preparation prior to TXRF, and after that we show different applications of nanosolvents developed in our group, including magnetic nanosolvents, nanostructured noble metals, graphene membranes, and noble metal nanoparticles immobilized in cellulose filters. The determination of metals is a key issue in analytical chemistry, since some of them are essential for life and others are toxic, even at very low concentrations. Thus, the trace and ultra-trace analysis is of vital importance. For requiring usually efficient sample preparations approaches, simultaneous multi-elemental analysis, fast, sensitive, robust, and precise analytical techniques, which is also important, the on-site analysis, having transportable instruments. For example, for the evaluation of metal pollution, to study the bioaccumulation through the food chain, and also in quality control processes. The current analytical instrumentation allows the determination of elements at very low concentration. However, it is still often necessary to apply separation and preconcentration strategies prior to quantitative determination. For example, this is the case of TXRF, Total Reflection Array Fluorescence Spectrometry, that has several advantages, such as the simultaneous multi-elemental analysis, the suitability of dealing with microsamples without the requirement of argon or cooling water, with decreased background and matrix effects, wide linear range, and easy calibration. However, the sensitivity of this technique is is an inconvenience to have under consideration. The development of TXRF was in 1985, with increasing popularity and becoming nowadays a well-established technique. In TXRF, the limits of detection are calculated according to this formula, using the concentration of the element, the background intensity, and the net intensity of the selected elements in the spectra. This figure typically represents the limits of detection achieved by TXRF according to the atomic number. In the tables on the right, we calculate the limits of detection for certain elements using multi-elemental standard solution. As we can see in the second table, the limits of detection can vary from 0.7 to 2.2 microgram per liter. If we compare these values with the maximum contaminant level allowed in drinking water according to different organisms, some of them are lower than the limits of detection achieved by TXRF, thus requiring the development of preconcentration techniques adapted or suitable specifically to TXRF in order to improve the detection limits. Some of the causes for these worse detection limits can be the selection of the low-intensity lines, the loss of elements by volatilization produced during sample drop evaporation, the problems of overlapping peaks and interferences. Thus, in general, preconcentration strategies provide an increase of the concentration of the target analyte into the extractant phase, thus producing an analyte enrichment and improving as a consequence the limits of detection. Preconcentration also produces the reduction or removal of interferences, and it allows the trapping of volatile elements. Microextraction and preconcentration strategies derive from the classical analytical extraction techniques, liquid-liquid extraction and solid phase extraction. Liquid-liquid extraction is based on the analyte distribution between two immiscible phases due to the different solubility of the analyte and the matrix. In the conventional mode of liquid-liquid extraction, the analyte used to be an organic compound or a metal chelate, which is extracted into the organic phase, and then it is analyzed by the corresponding analytical technique. Solid phase extraction is based on the retention of the analyte from an aqueous solution into a sorbent or a solid phase. Mainly, there are two objectives in solid phase extraction that are analyte enrichment and sample cleanup. Another technique that derives from the solid phase extraction is solid phase microextraction, SPME, where a fiber of fused silica is recovered with a polymeric stationary phase and allow the extraction of different analytes. Usually, in these both techniques, in solid phase extraction and solid phase microextraction, the analyte elution from the sorbent is required before analysis. In the case of solid phase microextraction, this desorption is performed by the addition of organic solvents or by thermal desorption, since typically the analysis is performed by gas chromatography and HPLC. Solid phase extraction is a low-cost technique with simple configuration that provides a fast extraction. The typical or classical solvents used in solid phase extraction are normal phases, reverse phases, and ion exchange phases, as we can see in the slide. Additionally, there are two modes of extraction, dynamic and static. In dynamic mode, also named column mode, the solvents are packed into a column, a cartridge, a disc, or a pipette tip, and the sample is loaded through this solid phase extraction, producing thus the retention of the analytes onto the sorbent. Then it's necessary to perform dilution of the analytes from the sorbent to do the analysis. In a static mode, also named batch mode, the solid sorbent is usually a powder that has to be that is in contact with the sample solution. During the stirring, the retention of the analyte into the sorbent is produced. Then we need to, once the retention is performed, we need to make a separation of the solid sorbent enriched with the analytes from the aqueous sample. So typically centrifugation, filtration, and sedimentation can be performed for this phase separation. Additionally to the phase separation, elution of analytes have to be done by the corresponding eluent. Recently, nanomaterials have been used in sample preparation in analytical chemistry, mainly as sorbent phases, due to the different properties in comparison with conventional materials, such as the high active surface area and high adsorption capacity, among other properties, for example, like the high porosity of the presence of active groups into the surface of these nanomaterials. With the aim mainly of analyte separation, removal of interferences, and increase of the sensitivity. Thus, the incorporation of nanomaterials as sorbent phases allow to increase the sensitivity and selectivity, and as a consequence, the detection limits. In this slide, we can see a classification of nanoparticles in three types: noble metal nanoparticles of silver, gold, and palladium, for example. Then we have the metal oxide nanoparticles that we can classify as magnetic, for example, magnetite, and non-magnetic nanoparticles, such as titanium dioxide. Then we have the carbon-based nanoparticles, for example, carbon nanotubes, graphene oxide, or graphene. In addition of using nanomaterials, the preconcentration strategies, or extraction and preconcentration strategies, have evolved to miniaturized techniques by a drastic reduction of the organic solvent from 50 milliliters, for example, in liquid-liquid extraction, to only a few microliters, using single drop microextraction and dispersive liquid-liquid microextraction, and also by reducing the amount of solid sorbents used in solid phase extraction from grams to milligrams or micrograms, using the techniques dispersive microsolid phase extraction and thin film microextraction. It is also important to remark that low generation of radius is produced as a consequence of this miniaturization of preconcentration techniques, fulfill the requirements of green analytical chemistry. The static or batch solid phase extraction with conventional materials, in this case the sample and solvents are mixed. However, recoveries can be lower than 100% due to the aggregation of the solvent and also due to the incomplete desorption of analyte from the solvent. When nanomaterials are packed into dynamic solid phase extraction, there are some problems, such as the high back pressures that can be produced, and difficulting thus the high flow rates. As a consequence, if we use low flow rates, larger extraction times are produced, which is also undesirable. Thus, an alternative can be the use of dispersive microsolid phase extraction in combination with nanomaterials, since they provide they are well-dispersed phases that allow the higher extraction or efficiency, allowing the chemically or physically dispersion by means of addition of reagents or ultrasound energy, using a smaller amount of solvent and also a small amount of sample. The steps followed by dispersing microsolid phase extraction are similar to batch solid phase extraction. We have to remark that the lower amount of solvent is used in the range of microgram or milligram. After addition of the solvent to the sample solution, this mixture is dispersed by stirring or ultrasound energy, and the retention of analytes onto the solvent is produced. Then, two steps are necessary to be performed. First, a separation of the analyte enriched solid phase from the aqueous sample solution by centrifugation, filtration, or sedimentation. Once the solid solvent is separated, then we need to perform the desorption or elution of the analytes from the solvent to a new aqueous solution or to the eluent solution. And then we need to separate again, once the elution was performed, the solid solvent from the eluent with the analyte, because some techniques we need to do the analysis into a solution instead of a solid sample. Sometimes these nanoparticles can be reused. However, dispersive microsolid phase extraction has some problems, such as the loss of the nanomaterials during these separation steps, mainly filtration or centrifugation. Thus, an alternative could be the use of magnetic microsolid phase, such as these magnetic nanoparticles, that has different advantages, such as the easy dispersion of the nanoparticles and easy separation of the nanoparticles from the aqueous solution by using a magnetic external field. Also, it is possible the modification of these nanoparticles by functionalization, for example, and also it is sometimes possible the reutilization of these nanoparticles. Mainly, if the desorption is complete, we can reuse or reutilize the nanoparticles of magnetite for another extractions, if also they are not damaged during the desorption step. In the slide, we can see the scheme of the procedure developed. First, the microsolid phase magnetite nanoparticles can be added to the sample solution, or they can be directly prepared after addition of the precursors. And after agitation or ultrasound energy application, we have the nanoparticles synthesized if we add the precursors, and also the analytes bonded, the analyte bonded to the magnetic nanoparticles. Then we have to perform the separation of the magnetic phase using an external magnetic field, as we can see here. And then we have two possibilities. If we made the direct analysis, we can also do this analysis with ETAs or TXRF, which are suitable for a suspension or a slurry sampling. However, other techniques like ICP-MS or ICP-OS, we need to do a desorption or a dilution of the analyte, for example, by diluting nitric acid is the typical eluent use. And then we analyze the eluent by these techniques because they don't allow the use of particles. In this slide, we can see the comparison of the use of non-magnetic solvents and magnetic solvents. By these both techniques, dispersive microsolid phase extraction and dispersive magnetic microsolid phase extraction. As we can see in the first part, we see more steps if we use non-magnetic solvents. For example, as we can see, the phase separation is performed by centrifugation, sedimentation, or filtration. However, this step is replaced by a fast phase separation using the magnetic external field, usually with 5 minutes or separation is enough for a complete separation of the magnetic nanoparticles from the aqueous solution. And also we can see the different techniques that we use. For example, also for the TEM microscopy, usually the suspension of the particles is used, but we need to perform a dilution because they are very much concentrated for this technique. Then we have the thin film microextraction, which is a new geometry or format of a solid phase microextraction developed in 2003 by the Paulissing Group in Canada in order to improve the sensitivity and extraction efficiency by increasing the volume of the extractant phase and reducing the thickness of this phase. In this case, usually a membrane is used. As we can see in the slide, there are two modes of thin film microextraction, as in solid phase microextraction, which are thin film immersion and head space thin film microextraction. In the case of direct immersion, the solid phase is in direct contact with the sample, and the stirring of the solution allows the transport of the analytes from the sample solution to the thin film. In the head space thin film microextraction, the target analytes have to be volatile or semi-volatile. Sometimes a derivatization step could be used to volatilize these elements. Thus, the solvent is in the upper part of the vial, as we can see in the head space of a closed vial, to avoid losses by volatilization. In the slide, we see the thin film developed in 2003 and also the configurations developed in our group. For example, if we use the head space solution, we use different possibilities. One is to place the quartz sample carrier in the upper part of a sample solution containing the analyte, having a head space for allowing the trapping of the analytes that moves from the aqueous solution to the head space and then from the head space to the acceptor phase, which is usually a thin film of nanoparticles. And also we have another example using suspended or floating membrane, for example of graphene that we are going to talk about after that, which is a membrane like this, like a disc, and it is flexible, and so when we agitate or stir in the solution, the vortex formed in the vial allow to place the membrane in this part. So the stirring also facilitates the transfer of the analyte from the aqueous solution to the solvent. In relation with the sample preparation prior to TXRF, it also depends on the configuration of the instrumentation. As we can see, there is a small distance between the sample carrier and the detector. So the sample has to be prepared as a thin film or layer of a thickness of maximum of 100 micrometers to avoid the damage of the detector and also to have quantitative analysis. As we can see in the slide, there are different possibilities of drying the drop once it's deposited onto the quartz sample carrier. Usually an internal standard was added, as we talked at the beginning. After deposition, then we have to dry this drop by the different possibilities in a hot plate, under infrared lamp, or also in a laminar flow box to avoid contamination. This is an example of the aspect of the carriers. As we can see in this scheme, there are a lot of possibilities for sample preparation prior to TXRF, for solid samples, liquid samples, and also for gases. Probably the most common sample preparation strategies were the preparation of a suspension, the mineralization by acid digestion, also the extraction procedures, and it is also important to have under consideration the direct analysis of solid samples, for example, as thin slices of tissues, or also without treatment or with minimal treatment, that can be, for example, dilution of aqueous solution. Thus, if we use nanomaterials for TXRF, we need to prepare them according to this to the mentioned above. It means by using a thin layer of nanoparticles, as we can see in the slide, of a lower thickness, and they have to be adhered to the quartz sample carrier, since the analysis with this technique is performed in a vertical position. So we need to fix these nanomaterials. In the slide, we can see the different examples of our works. For example, this one is the graphene membrane, so we can see that it is very thin. So we have no problems with the detector. Then we have the magnetite nanoparticles and also the cellulose filter modified with silver nanoparticles, which is sticked or adhered to the quartz sample carrier. In our research group, we use mainly 3 types of sorbents, as we can see here. First, magnetic nanosorbents, including magnetite, magnetite modified with manganese oxide, magnetite in presence of noble metals. Second, nanostructured noble metals of silver and palladium, and three, membranes of graphene and cellulose filters containing noble metal nanoparticles. We tested several nanoparticles of silver, palladium, and gold, but this application is with silver. And we use different microextraction techniques. Dispersive magnetic microsolid phase extraction for these magnetic nanosorbents, and then thin film microextraction in both modes, head space and direct immersion. And in the final work, we use filtration. We developed here an in situ sonochemical synthesis of magnetite in presence of the sample solution containing all of these target analytes. In this case, it is very interesting because we integrate all the steps in one. It means we perform the synthesis of nanoparticles while or simultaneously we preconcentrate the target analytes into these magnetic nanoparticles. Because this synthesis is very easy. In the first case, in a vial, we add the chloride salts of iron 2 and iron 3 in presence of sample solution or standard solution, and we add ammonia. Then we have to sonicate in a cap horn sonoreactor for 5 minutes, and at the same time, you can see that the nanoparticles of magnetite were formed by coprecipitation, and also some of the elements are trapped by occlusion, and other elements can be added by surface adsorption to these magnetic nanoparticles. Then we have to perform the separation of the nanoparticles enriched with the target analytes from the aqueous solution, using in this case a magnet, an external magnetic field that we can see in this slide. After separation during 5 minutes, it is necessary to perform the washing of these nanoparticles because they have media containing high concentration of ammonia. So we did, I think, 3 washing with ultra pure water, and then we can have the nanoparticles. And we only deposit here in the quartz sample carrier a few microliters of the magnetic nanoparticles, and then we add the internal standard. After aqueous drop evaporation, we perform the analysis by TXRF. However, these naked magnetite nanoparticles have a high chemical reactivity and can be oxidized by air, resulting in a losing of magnetism. Thus, could be also interesting to improve the laser extraction obtained by these naked nanoparticles by using, for example, another metal oxides that have higher adsorption for metals. that is manganese dioxide. In this case, we use the analytes also showing in this lower part, and we use the magnetite nanoparticles as the core of the particles recovered with a shell of manganese dioxide. The synthesis consists only of addition of potassium permanganate and polyethylene glycol to a few microliters of magnetite to the sample solution. And here we use the ultrasonic probe only for 30 seconds since it is more powerful than the cap-horn sonoreactor, and the co-precipitation of the elements is produced. In this table, we can compare the limits of detection and the enrichment factor achieved by these two types of magnetic nanoparticles, magnetite and magnetite recovered with manganese dioxide. As we can see, the limits of detection are improved in all cases. For example, in the case of copper, vary from 0.4 microgram per liter to 0.24 microgram per liter. Additionally, the enrichment factor can be improved in some elements by a factor of 10. For example, thallium from 45 to 416. So we can see an improved enrichment factor and detection limits using manganese dioxide. To sum up, we can see that this synthesis is very easy and it produces an integration of steps, having the synthesis and extraction of analytes in only one step. So the analytes can be trapped by occlusion during the co-precipitation of the magnetic nanoparticles, and other elements can be trapped by the surface adsorption to these nanoparticles. Additionally, no filtration and centrifugation is required because of the magnetic easy separation, and also elution is avoided because the TXRF analysis allows the analysis of this suspension of the magnetic nanoparticles. Also, we are going to have one drawback, which is the appearance of an intense peak of iron at 6.40 kiloelectron voltium and also double energy, 12.8, that overlaps some peaks, and the elements below these energies cannot be detected. Here in this slide, we can see these peaks of iron that we are going to comment at the end of this slide. A new or further research of magnetite derived from the previous one consisted of the use of noble metals, palladium, silver, and gold in presence of these precursors of magnetite, of iron 2 and iron 3, and also in presence of mercury as analyte. We can see that in that case, palladium shows the better extraction, allowing the efficient trapping of mercury into this magnetite. In this work, we use the direct mercury analyzer to perform the study of this procedure. However, we use TXRF as a characterization technique to see what happens with the mercury. For example, as we can see in the spectra, if we use without using palladium, mercury cannot be detected. On the contrary, if we use palladium in solution, I think it's 1 in a proportion in a ratio 150. It means not sure. I think it's 100 ppbs of mercury in 5,000 ppbs of palladium. So we can see the peak of mercury in that case, showing an efficient co-precipitation of trapping in presence of palladium. Here we can see the peaks of iron, which are also higher, dificulting the analysis of elements at these energies, and also double energy. And then also we have the molybdenum peak corresponding to the X-ray tube. In another publications of our research group were related with the generation of volatile species. It means hydrides and mercury vapor. As we can see in the slide, this is the scheme that we follow. We have a gas-liquid separator, peristaltic pumps, and different tubes. And one tube is used for the sample introduction into the gas-liquid separation. And then we have another tube with the reducing agent, which is usually sodium borohydride in presence of sodium hydroxide to stabilize the solution. And it is important to remark that also the sample solution has to be a high concentration of hydrochloric acid, usually 5 or 10% volume of hydrochloric acid. Then also in this gas liquid separator, we use argon as a carrier gas that moves these hydrides or mercury vapor generated from this gas liquid separator to the part where the nanoparticles are immobilized into the sample carrier with another tube. And this is a closed system that we can see a detailed scheme into the figure on the right. Here we see how the volatile hydrides or mercury vapor arrive into this part, this conical part, which is a polypropylene tip of a micropipette. And when it is closed, we see that there are no losses of these gases, and these vapors are trapped onto these palladium or silver nanoparticles. It depends on the work. In the first work, we have silver nanoparticles that were prepared by reduction of by chemical reduction using sodium borohydride, that it was added dropwise, drop by drop, to a nitrate, silver nitrate solution. Then these nanoparticles were added to a quartz sample carrier previously silanized and also using a silan compound. After interaction during 1 hour, this film was washed, allowing only to have the nanoparticles add to this silan. Then, using the scheme explained in the previous slide, we can see how the generation of volatile species is performed. In this case, we use 15% of hydrochloric acid as reduced as in the sample solution, and 0.6% mass volume sodium borohydride as reducing agent. And here we can see also the different rates, flow rates of the sample, the reducing agent, and also the argon, which is the carrier solution. Sorry, the carrier gas. Then, then after generation of the volatile species, these vapors are retained onto these silver nanoparticles as hydride of selenium and also mercury vapor. And they were retained by two different mechanisms. In the case of mercury, is produced by amalgamation, and in the case of selenium hydride, is produced by catalytic decomposition of this hydride onto the silver nanoparticles. In a similar work, we have these palladium nanoparticles, in this case, that were prepared by reduction of palladium-2 as palladium nitrate in the presence of ethanol water. After reduction of these nanoparticles, they were prepared in a silanized quartz sample carrier using the same silan as in the previous work. After interaction during 30 minutes, the film was washed, allowing only to have the palladium linked to the silan. Then the volatile species were generated, in this case, with a more concentrated acid and in a similar concentration of sodium borohydride. In this case, the hydrides of arsenic, of antimony, and bismuth were generated, and this vapor were trapped onto the palladium nanoparticles that are also retained by catalytic decomposition of the metal hydrides, as in the case of selenium. Then, using the same palladium nanoparticles, we have another application. Instead of using the sodium borohydride as reducing agent, here we use the photochemically generated mercury. For this reaction, we need as precursor for reducing a species formic acid or acetic acid, and also ultraviolet radiation. And then we perform two tests. First, in batch or discontinuous mode, we have the thin film of the palladium nanoparticles that we place in an inverted position over the headspace of a vial containing the sample solution or standard solution in, for example, formic acid. And then we have to put this vial with this sample carrier into an ultraviolet lamp to produce the generation of the mercury vapor, which is also moved, it's in the headspace, and then it's moved to the thin film of the palladium nanoparticles, which are then analyzed by TXRF. This system can be improved by especially the sensitivity by a factor of 10, as we can see with the online method. In this case, the sample solution and the precursor, in this case, we see that they were very similar, the formic acid or acetic acid. So finally, we use acetic acid because it's less toxic than formic acid. The sample and the precursors are moved through a peristaltic pan and through to the lamp, ultraviolet lamp, generating the vapor of mercury, which is moving to the gas-liquid separator and trapped in the same system as described in the previous slide into the palladium nanoparticles. Here, the enrichment factor obtained for mercury was of 127, less than in the previous publications, using this hydride generation. However, this has the advantages of now using sodium borohydride, which have different problems, such as the high amount of hydrogen generated, the low amount of residues generated also, and the instability of this sodium borohydride solution that needs to be stabilized with sodium hydroxide. Another work we performed was in relation with graphene membranes. Thus, we prepared these membranes based on the Hammers method. As we can see in the slide, we begin with the graphite powder, which is then oxidized to graphite oxide, and then it is exfoliated by ultrasound energy to graphene oxide, and finally it is thermally reduced to obtain graphene. As we can see here, these are how to prepare the membranes. We have this graphene oxide here, and we deposited onto the glass substrates of this size, and then we have to dry around at around 80 degrees during 8-10 minutes, and then we have these black membranes. We take this and we put into a glass containing water, because these membranes have this property of floatability in water, and we save in this way before analysis. Here we can see how this membrane acquires this conical form during agitation in this vortex form in the sample solution. And here we can see how with these tweezers and the glass substrates we can manipulate or handle this membrane. And we use these graphene membranes in direct immersion thin film microextraction for the extraction of chromium-6 at very acid pH. And another application we have is by using complexing agents such as ammonium pyrrolidine dithiocarbamate, which is a typical metal chelate, and we form a chelate with all of these elements, and we are able to preconcentrate them into the graphene membrane of cobalt, arsenic, lead, gold, nickel, selenium, mercury, and also bismuth. In this slide, we can see the spectra obtained for different graphene membranes. As we can see, the background is very low. Additionally, we also can see that a sulfur peak is observed due to the presence of APDC as metal chelates. And in black, here we can see the target analytes. Also, we have some elements that appear due to the different sources. For example, the manganese is used as potassium permanganate for the synthesis of graphene from the graphite powder. So because of this, probably we have this peak. Also, the peak of iron could be coming from the drying of the drops into this part. When we have here the drying of the thermal reduction of the graphene oxide to graphene. Probably the iron comes from contamination comes from here. And also we can see the peak of molybdenum. Another research work derived from the previous one was based on the head-space thin film microextraction. In this case, we analyzed this compound, this organic organometal compound, methyl cyclopentadienyl tricarbonyl manganese, MMT, which is an octane enhancer using fuel. So it is interesting to determine sometimes this concentration in some environmental waters. So here we have the sample solution, and in this upper part we have the quartz sample carrier. with a graphene membrane immobilized in this in the interior part, exposed to the headspace of the solution. Here, while stirring and warming, we were able to extract the MMT from the aqueous solution to the headspace, and then they were retained into the graphene membranes. However, the extraction efficiency can be improved by placing this laboratory-made system to cool the membrane in the upper part. It allows to obtain enrichment factor of around 265 in the case of these organometallic compounds. In this case, the interaction is due to this cyclopentadienyl as P interaction with the graphene membranes. One of the last works related with TXRF was performed with the filters or cellulose filters modified with silver nanoparticles. Here we can see the preparation of these filters. We have the silver nitrate, then we need to wash the filters with ethanol to remove the possible silver not retained into the filter. Then we perform the reduction with sodium borohydride, and finally we wash with water. And we have to air dry the filters to have this aspect. We have in this work here also we can see how the filter nanoparticles is stick to the TXRF carrier before the analysis. In this work, we use the TXRF as a screening of the elements. It means that we perform the filtration of different elemental solutions, and we can see here that, for example, in the case of mercury, we observe a better signal, allowing that the mercury can be trapped by amalgamation into these filters. Since the direct mercury analyzer provides a better sensitivity for mercury, which is specific for mercury, then we perform the work only with DMA, but we use the TXRF for this screening. In this slide, we can see the spectra obtained for these cellulose filters after filtration of a solution of mercury. So we can see these high peaks corresponding to mercury. In this slide, we can summarize the different spectra obtained for the nanoparticles studied here. We can see that, for example, in gray color, we can see the background of graphene, which is the lowest, the graphene membranes. Then we can see that for palladium nanoparticles, silver and cellulose, we have similar background, and also we have to remark that the palladium and silver appear as small peaks when we use these nanoparticles, but they do not interfere in the analysis. However, the iron corresponding or coming from the magnetite, we can see a high peak, so maybe they overlaps another elements. We can remark that, for example, better enrichment factors were obtained when using magnetic nanoparticles and also with palladium and silver nanoparticles. Here we summarize the detection limits achieved by all of these techniques. As we can see, all of them improve the limits of detection instead of without using nanoparticles. As we can see, for example, some of them are very low, 0.05 microgram per liter for mercury, which is also very interesting. Finally, in our group, we show the usefulness of TXRF as analytical technique, but also as a screening technique at the beginning of the procedure and also at the end of the procedures for the characterization. Thus, the combination of nanomaterials for preconcentration strategies allow to improve the detection limits, they allow to increase or obtain high enrichment factor, and also trapping the volatile analytes. Since TXRF allow the direct analysis or suspension on membranes, we avoid the settling, centrifugation, filtration steps for phase separation, and also we avoid elution of analyte from the solvent. That's all, and thank you for your attention.
Okay, Inma, thank you very much for this nice presentation and to share with us all of your experience. And yeah, it has been a very good overview about the possibilities of preconcentration in combination with TXRF. So now is time for questions. I don't know if some of the assistants has some questions for you or some curiosities. Let me check the list if there is somebody that want to ask something. No? Okay. Sorry, but I have a couple of questions for you.
So
Yeah.
I have a question too.
I also have a question.
Okay. Sorry, I didn't see your hand. Okay.
Yeah.
Please go ahead.
Hello, Inma. It was a great presentation. I really enjoyed the presentation. I have some questions. The first question is I am really curious about that single drop micro extraction technique. Could you just elaborate about how this single drop micro extraction technique can be performed with sample size? You told that within 5 to 10 microliter only.
I'm going to move to the
Initial part of the presentation.
Yes. Well, I only have to here a little bit. Here. Okay, thank you for your comments. In relation with the single drop microextraction, there are different modalities also. We have the mode in head space. If we have here, for example, an aqueous solution, and also here an aqueous sample. So we can use this mode. However, if we have an organic solvent, which is also insoluble in the organic phase, we can have immerse the single drop directly immersed into the sample solution. So it depends on the analyte. If it is organic or inorganic, we need to select the proper solvents to perform this single drop microextraction. We didn't have any work using this technique for TXRF. I think Eva have some publication of this with trichloro, I don't remember exactly, with an organic solvent, trichloromethan or something like. I think that you use a PDC complexes and also you extract with something like this with organic solvent. So it could be a possibility. I don't know
Yes.
how it's difficult to dry into the TXRF. So maybe Eva, you can say something or.
Okay, I mean, my experience in microextraction is mostly using dispersive liquid-liquid microextraction and also hollow fiber, but not single drop. Yeah, so yeah, I think that it's I don't have experience, but according to some colleagues, it's quite difficult because it's only a drop in the system. I mean, the precision is not really good, I think. But yeah, I never tried.
Yes, in my group there is another colleague that works with this a lot from the PhD and so on. So he has a lot of experience on this, and it is also, as Eva says, the precision is very bad. So you need to try a lot to be able to do this, because sometimes the drop fall from the seating. So I tried several times and I'm not very prepared for this.
Okay.
But you can also check depending on the analyte, on the solubility on the solvents, and depends also on the technique you use. For example, for electrothermal atomic absorption spectrometry, some applications exist with the single drop microextraction, and also for ultraviolet spectrophotometry, I think. So there are a lot of possibilities.
Okay, so there are a lot of possibilities using this technique. And another question I also have, you have used that membrane-based preconcentration methodology for the preconcentration of mercury, I think. So you have used a thin film of membrane for the preconcentration purpose, but how do you normalize it, or how what is the internal standardization that you have used in these types of sample preparation methodology?
I think that usually I don't remember exactly, but usually we use gallium as internal standard.
So you put gallium directly on top of that membrane?
Yes, here, yes.
Not this one. It is almost in the last part of your slide. You have used a thin film of membrane.
This here. I think we use in the same case with the graphene membrane. In this case, also we have the graphene membrane adhered to the quartz sample carrier, and then we add the internal standard of gallium.
Okay, just on top of it you put.
Can
You
you
put
repeat?
you put gallium internal standard just on top of it.
Yes, yes. Then and you need to leave the drop has to be evaporated. Also, this drop.
Because I have tried this technique, but I have got poor precision. But I don't know why. I have tried it, just dropping that, but the precision I have got was not that much. Maybe I'm doing some mistake. I have to see.
Yeah, you need to be with the arm and stick to the table to yes, to be careful to deposit the drop.
Sometimes I also tried with the scattered relay or compton scattered pig I have used as an internal standard. But yes, I will also try with other internal standard. Yeah.
Also in some applications, not described in this presentation, but the work I performed during my PhD, we use slurry samplings. So in an Eppendorf, we have to add the solid sample, then the Triton X100 for the suspension, and here I also add the internal standard. Instead of adding to the sample carrier, we add into the vial, and we mix the internal standard with the sample.
Yeah.
But here is not possible because the internal standard didn't migrate to the solid phase in the same way as the analytes.
Okay. Thank you.
The difficulty.
Thank you, Emma.
Thank you.
Okay. Yeah. Thank you for your answers. I think that Ursula has also a question for you.
Yes, now I raised my hand properly. Yeah, thank you, Inma. Very interesting subject, very nice talk. I have a question to the graphene membrane as well. It seemed to me from your conclusion that this gives the nicest spectra, so this would be a very nice method for the TXRF. And so towards the preparation of the graphene membrane. So the last step of the preparation was the reduction, but then in the following slides, there was some oxidized groups that were used to collect the metal ions, and there were also some derivatization, I think, with some complexing ligands. So after the reduction step, was then there another preparation step to introduce again groups?
Thank you, Ursula. No, we didn't perform another another preparation step, but here the thermal reduction is not complete. It's partially reduction. So some groups of the carboxyl or carbonyl and alcohol remain into the membrane. So it is not complete this reduction, and because of this, there are some groups that can interaction with the, for example, chelating agents of the APDC.
Mm-hmm. Okay.
So it's partially reduced. So maybe yes, I have to explain here, but it's to summarize, but it's partially reduced.
Okay, and then the ligands, they are just given into the solution and then they interact with the metals and the membrane. Is that correct?
Yes, we studied this thermal reduction. We use we have optimization of this procedure, so we analyze. I'm going to try. We perform this reduction by different times. For example, 1 minute, 2 minutes, 3 minutes, 8 minutes. So and then we use these membranes for the extraction for the metal chelate with APDC, and we can see what is the perfect or the most suitable reduction of the membrane according to this complexation.
Mm-hmm. Okay.
So I'm not sure exactly how it works, but I think it's something like you say. And also
okay.
the membrane, the graphene, there exist p interactions of these pentane groups with the, for example, cyclopentadienyl or the APDC that has also electrons, p electrons.
Mm-hmm. Okay. Yeah, thank you very much.
Okay, any other questions? because I'm checking, but I cannot see any hand. Okay, so perhaps I can ask now a couple of questions. One of my questions is also regarding these membranes, because I realized that they are quite, I mean, which is the diameter of these membranes? I mean, they are completely irradiated with the X-ray source, or you analyze completely these membranes?
I think it's bigger.
It's bigger, yeah. Because then my question is, if you checked, for instance, the homogeneity of these membranes or how the analytes are distributed, because if you are not analyzing the whole membrane, perhaps then you can have some, I think, reproducibility problems somehow if the membrane is not really homogeneous. I don't know if you have tested something about this.
Yeah, I think that I don't remember exactly, but I think I remember to perform these studies by placing the quartz and then by, ¿cómo se dice?
You mean rotating? What?
Yeah, moving the disc. O sea, I made analysis, I moved the disc, I don't remember, okay. 20 degrees or something. Yes. But I don't remember exactly. I think that they are different sometimes, but not a lot, but not very different. They are more or less homogeneous. Okay. And then we have problems with the TXRF, so we didn't finish these experiments, and I think we didn't put in the publication.
Okay.
Because I think at the beginning of this work, the detector was damaged.
I know what's that. That present hour detector is also crashed and is being repaired, so I know that sometimes, yeah.
A problem, yeah.
Yeah, and and the last question, because you have put a sort of summary at the last slide about the potential and possibilities of the different types of nanomaterials and microextraction approaches. But looking at this summary, what do you think? I mean, which is the best approach regarding the nanomaterial, for instance? Because I've never worked with magnetic nanoparticles. All of my publications are regarding the carbon-based, because there are no peaks there, only the analytes. So, but I don't know, according to your experience, what do you think?
Yes, I remember that we have something to work together, no? But
yes.
I don't know when is going to be the time, but probably near.
In the near future, we hope,
I think, yes. But the magnetite has the advantages of the easy synthesis and at the same time the trapping of the analytes. The problem could be, for example, the Kapp-Hornsonor reactor, it is a little bit older, and now it is not effective as at the beginning. So maybe we need to buy another one or something like this. It could be a problem. And in relation with the spectra, also the manganese also has some peaks, as we consider are very large peaks in this part. But maybe if the target analytes are here, here there is no problem. I don't know, with your detector, I remember, do you have the wolframium detector?
Yes, we have also this, yeah.
So maybe we can analyze.
I mean, it's a difficult question because there are not a perfect method for all the analytes, all type of samples. You already know this. So sometimes, you are right. Depends on the purpose of the,
maybe
of the analysis.
This is simpler than the hydride generation because you need two peristaltic pumps, the gas liquid separator to be performed in a hood because the hydrogen generated is also toxic. So for example, for students, it's easier the magnetite, for example, for a PhD degree or something like that.
Yeah. Okay, thank you, Imma. So this is the last chance for a question, if there is still some, No, I think that everything is clear now. So I want to thank Imma again for this nice presentation. And because the summer is coming, now the next session of the TXRF Club will be postponed until September, so we will have a sort of summer break. I don't know if Ursula or June want to say something also. They are the organizers of the TXRF Club.